Hi, nice to meet you on our YouTube stream. My name is Andrei Mazhey. I am Chef Technical Officer of Mechatronics. It's not traditional webinar when everyone can talk, but you can post all your questions in the chat and I will try to answer. You can always rewatch the video on this YouTube stream as well. Our company Mechatronics produce different sensors for GPS tracking industry and of course popular fuel level sensors as well. Because remote fuel consumption monitoring is a very important part of GPS fleet tracking. Our fuel level sensors are called EuroSense Dominator. There are a lot of different modifications, different interfaces, wired and wireless, a lot of different features and modular design. While selling and supporting fuel level sensors, we are facing a lot of same questions from different customers regarding tank calibration. Like, do you have fuel level sensor to install without calibration? Because filling tank by portions is very time consuming. Or do we need to calibrate tank by portions if we did empty full calibration? On this stream, I'd like to give you more information about basics and what tools we can provide to make your installations simpler. What's the difference between calibrating the sensor and calibrating the full tank? Many people confuse these concepts. What is sensor calibration? It normally refers to capacitive fuel level sensors and not ultrasonic or radar ones. As a result of measurement, capacitive sensor gets abstract number, abstract value, and this value grows when fuel level rises. We can use it as the result of measurement. For example, we have sensor with default factory length of 700 millimeters, and in empty condition this abstract value is equal to 6,600 units. It grows with fuel fillings, and on the full tank it reaches like 11,000 of abstract units. If we will take a longer sensor like 1 meter, these values are bigger, and for shorter sensors these values are smaller. It's just not convenient. We'd like to see sensor output equal to 0 on empty tank and have fixed value on full tank. It's just more user-friendly because based on these values we are making tank calibration. And so that's why we have internal sensor value and external sensor value. Internal value is the result of measurement, this one, and external what sensor sends to your GPS tracking device. And what's tank calibration? We just make relations between them. We teach sensor that this value is going to be 0, and this value, please give us for full tank, we want to see 1023, for example, or can be any value like 10,000. Please give us this exact external value on full tank. And by default, sensor from factory is pre-calibrated. So we are getting these values, but we need to fit the sensor in the tank. And after cutting these values are reduced, and from this output range of internal values we will get this one. And on full empty tank, cutted sensor will give not 11,000 but only 9,600, and based on stored calibration table and sensor factory calibration, we will get not 4,000 but this value. It's not a problem at all, in fact, but problem empty tank because 0 was for previous calibration, and our current value is much below this. So sensor should send negative value to GPS tracking device, but problem that GPS tracker cannot receive negative value from fuel level sensor. So sensor will send 0 until fuel level increase factory calibration data. And this range between these values is blind zone. So we cannot calibrate the tank correctly using such calibration, because first added portions from 0 tank to some amount, we will still get in 0. And that's what sensor calibration stands for. We teach the sensor of its new height or length. After sensor calibration, sensor restore its default output range, and no matter how we cut or extend the sensor. And calibration doesn't mean always immersion sensor in the fuel. We have some tools in our configurator to skip this procedure in most cases. Now about tank calibration. You know this procedure as filling tank from empty to full by portions, also as time-consuming procedure. That's why we often ask it if we have a full sensor can be installed without this procedure. Problem that sensor itself doesn't require tank calibration. This procedure refers to full tank. And there are different types of liquid level sensors. Capacitive sensors, pressure, ultrasonic level sensors. They are all level sensors, and natural output is level. There are no full volume sensors on the market. So if you or your customer can be satisfied with height or height percentage, you don't need to calibrate the tank. You can use sensor data already. But if you need volume in liters or percentage of volume, you need to teach sensor or your GPS tracking platform how to convert level to volume. And normally you are teach by entering the table and sometimes formula in your software. Typical tank calibration table contains fuel level with fuel volume information. So for any fuel level, we can look up fuel volume information in the table. And there are a lot of ways to get this table not using filling tank by portions. For example, a very time-consuming procedure of full tanker calibration could be done already by tank owner before your installation. For example, you can ask for tanker calibration chart, dipstick table. There are a lot of names, but idea is same. It's a paper sheet or Excel sheet or something else where you can find level and volume information. As you can see, we have 3 tanker compartments and 3 tables for each compartment. And we don't need, having this information, we don't need to calibrate tanker by portions. We can convert these heights into sensor values using our configurator tools. Also, tank calibration data may look like this one. It's a scale on the tank, like this one. In every case, it's a height plus volume information on different levels. We can convert all this information into ready sensor calibration, and avoiding this time-consuming fuel fillings by portions. If we put tank calibration data on a plot, we will get like a chart like this one. How sensor or your software platform calculates volume when level between our calibration points. Let's imagine that our points are connected by red straight lines between points. When new level measurement comes, the sensors look up by this chart and find this point on this imaginary red line and receives volume. And here is a very important outcome from it. A very popular question: how many points of tank calibration we should take? You may think that more points the better, because when you have more calibration points, as you can see, the red line is closer to real calibration chart of the tank. But in fact, it's not always true. At first, it depends on what equipment do you use for tank calibration. Cheap fuel counters don't like start-stop, and you can have like half a liter error per every portion. So when you're using cheap fuel metering equipment, smaller portions, 3-5 liters, may lead to less accuracy due to start-stop error. In fact, you can test it, you can make some comparison with your fuel metering equipment, try to fill like 50 liters with big and small portions and see the result. But do we need a lot of calibration points at all? For example, we have a rectangular tank. Its calibration chart will look like that. It's a straight line between empty and full tank. So what happens if we have only 2 points, empty and full? To calculate any value in between empty and full, sensor will look up for value laying on the same straight line. So no difference how many calibration points you did for rectangular tank. In fact, tank calibration chart can tell us about tank shape, and tank shape can tell us about possible calibration chart. Look on the real tank first, then imagine that you have cut it for thin horizontal slices from left to right side. It's a tank cross-section on different level. Then ask yourself, are the slices have same size? If you have same size of slices, you can use bigger step for tank calibration points. If for horizontal cylinder, we can't find same size of sections. They're all different. So we can't reduce the number of calibration points for horizontal cylinder. Another example, typical truck tank with mostly rectangular shape. As you can see, some parts, lower and upper, will give us smaller slices, and the main part of tank will give us like mostly constant cross-section on different levels. And that means we can do more calibration points in upper and lower parts, and make bigger steps and less points in between, in medium part of the tank. On calibration chart, this tank looks like this: small bottom and top roundings with more points, and bigger steps between because it's mostly straight line between them. And again, rectangular tank can be almost pure rectangular, and you can use only 2 points, empty and full, because all cross sections are the same. It can help you to choose the optimal number of calibration points. Very important that if we have a possibility of 2 points tank calibration, like this rectangular tank, we don't need to fill the tank till full condition to calibrate it. We can emulate full tank state by immersion sensor in the tube, like during sensor calibration. So we only need to know exact tank volume for tank calibration. And for rectangular tank, you can calculate it by easy school formula, or you can ask customer. So you don't need to fill this tank, you only need a tube with empty and full calibration points, and your calibration of tank is ready as well. By the way, regarding cylinder tank shape, yes, for horizontal cylinder we need a lot of calibration points. But what if we have vertical cylinder? How many calibration points do we need? If we will check the cross section, it's same for all levels. That means for vertical cylinder, again we need only 2 calibration points, empty and full. And again, we don't need to fill it till full to make the tank calibration. We can calculate the volume using school formula. So these kind of tanks are very easy in calibration because you don't need to do it physically. And now we know that tank shape is linked with the chart. And we can check if our team or contractors have made the calibration correctly. Several simple rules how to check full calibration plots. Rule number 1. No horizontal parts allowed. Horizontal line means zero cross-section of the tank. If you can see horizontal line on the calibration plot, it's an error. This error happens when you added new portion of fuel, but you registered same amount of volume in your table. And rule number 2, no vertical parts allowed. And that happens when you have added point in your table, like this one, without adding real fuel in the tank. So you forget to add fuel in the tank, but you added the point. And rule number 3, more general. Remember that every bend of calibration plot is a dramatic change of the tank shape. For example, a plot like this one. The slope of this line, tank calibration, in fact means tank width. And we can see that lower part of tank and higher part of tank have much bigger width than medium part of the tank. So if this calibration is correct, our tank shape is something like that, seen from like left side of front. It's very strange, and most likely it's an error. And in most cases, such parts are when you mistype the full volume added during calibration. For example, we have added 40 liters in the tank physically, but registered only 20 from them in the table. So now we have some general background to understand features and tools from Mechatronics configurator to make your installation simpler and faster. We have several tools in our sensor for it. First one is verification of the table. You can display the calibration tables on a chart and check them, and you can compare them between. Let me show how it looks. So I will load sample of calibration table. We can open it. We can see that plot is smooth, no like bendings or defects, and most likely it's okay. And we can compare it with other calibration plots, for example, of similar vehicles with same tanks. You can see that they are very similar. Very similar character, but you can see the difference between different calibrations. They are very similar, but not the same. And we can see some errors as well. Informs about error. I will show how it looks. It's a normal plot. and it's a plot with error. We can see a vertical part here. It's one of the bugs I described before it. So you can upload different tables of your staff or your contractors and notice errors before your customer will complain the wrong data. Another popular question, if you have many similar trucks, do we need to calibrate each tank again? Let's see the examples of several calibration tables from similar vehicles. Our first intention is copy calibration results from one object to another. But as we can see, we have about 10 liters difference on 2000 liters tank. It's a bigger error than we'd like to see. Why such difference? Difference in sensor, because each sensor, especially electrodes, has its own properties, and you cannot cut two different sensors in the same way. There are always some difference in it. Also, tanks are different. They have different height and different width. And three of these factors affect detector value, and width and length of the tank affect volume value in the table. So how we can solve that? We can get correct calibration table from first vehicle, knowing only first and last point of second vehicle. If we can see on the plots, we see that plots almost same, but it looks as if we can move first and last points of first calibration to points of second calibration, we will be fine. So let me show how it works in configurator first. So we have a table of first vehicle. We did real calibration by portions, and we'd like to move it to second same vehicle. We need to know empty and full sensor values, detect internal sensor values for empty and full tank. So we need to cut sensor and calibrate it in the tube for second vehicle. And we will know these detector values for second vehicle. After that, we can choose this point. Let's imagine our new value is 6400, and we choose this point and then move the plot to our new value. Same with endpoint. Let's imagine it would be 10,000. So we move this point as well. Okay. And now the most difficult part, tanks also different. And they have different volume. And our first tank was 210 liters, and second tank is 5 liters more. So we need to move this point upwards. Okay, and we save the changes, and now we have ready calibration for second vehicle. So resume how to do that. You're installing first sensor, calibrate the first tank by portions. Then you cut sensor for second vehicle. Then you measure detector empty full values for second sensor in the tube. Same as for sensor calibration, empty full. And very very good if you can know the exact volume of second tank, because it can be different from first one. Then you transform the table using our configurator and save into sensor. Here are some restrictions. Of course, full tank shape should be the same. So that means same model of vehicle, same tank. And the position of full tank should be same, because they can have some inclination when attaching to the vehicle frame. If there are different angles, it will not work. So next feature is how to use existing dipstick table or tanker table when you have already calibration data. This is extremely important when you're dealing with a big full storage. And as I said, data can be in any format: paper sheet, electronic sheet, scale on the tank itself, no matter. All you need to type this data in Excel in format level and volume in any units, inches, meters, no matter. Then you need to know again empty and full detector values of sensor, which you will fit in the tank. So you need a tube. You don't need to fill the big full storage, you need only to have a tube. And calibrate sensor empty full to know these values. And pay attention how it's going to be installed. On big full storage, typically you install sensor in the neck. And neck level is a bit higher than tank surface. That means when your tank is full, your sensor is not immersed fully into fuel. So you need to dip sensor during calibration on same level, leaving part of sensor outside the fuel. After dipping, you note the full and value, and then remove sensor, note empty value. So now we are ready to make calibration table. How it looks in configurator. So you open 10 calibration tab, mass calibration. Here is a button, load Excel file. Before that, we need to set up empty and full detector values. We obtained it just now during calibration in the tube, and a load file. And your calibration is ready. You can save it into sensor, and you don't need to make time-consuming tank calibration. Another important tool is mathematics, calibration of cistern tank in the form of cistern shape. In configuration software, you can find the mass calibration tab again, but instead of loading the file, you can put all dimensions. Again, during calibration, you need to follow same idea. Check how your sensor is going to be installed. Is it upper than tank surface or same level? So put these dimensions accordingly. How it looks in configurator. So we are entering our dimensions according to this picture, including this height above tank surface, and just put in our detector values from calibration and click calculate. So our calibration is ready, and we can save it into sensor. You can see if you enter dimension E equal to 0, you will get the calibration for horizontal cylinder without these side parts. So you can use this master also for horizontal cylinder calibration as well. And the last thing I wanted to tell you is how to get rid of sensor calibration. Remember, it was a procedure to teach sensor its new length after cutting or extending. And many fuel level sensor vendors recommend this procedure. First one, you cut the sensor, then you make sensor calibration in the tube, then you make tank calibration, and then you program table on server side. How it looks for EuroSense sensors. First one, you cut the sensor, then install sensor in the tank and make tank calibration using filling by portions using our configurator. And export calibration table to file. During this process, first and last points of calibration table are used for sensor calibration automatically. Because why we need to immerse sensor in empty and full when same sensor conditions we will have during tank calibration. So we just saving like 5 minutes for you. As a result, we have tank calibration in format we can upload to GPS tracking platform, and in sensor we have empty and full calibration, same results. So you don't need to bring this smelly calibration tube for installations when you are going to do real tank calibration by portions. But the tube is needed when you use another way of tank calibration, like mathematical calibration, loading existing table. So you will do either sensor calibration in the tube or tank calibration by portions. So I'm almost finished my story, and the resume, some most important moments. Sensor calibration doesn't give you volume information. It's only to adapt sensor to its new length, and by immersion into tube or by another methods. For EuroSense sensors, it's needed only if you will skip real calibration by portions, calibration of tank. Second, calibration table plot is linked with tank shape, so you can reduce the number of points by understanding the tank shape and how you can save your time. You can verify your installers and your contractors by checking calibration table results on plots, and especially if you can load several plots on same graph from same vehicles, you can easily find some errors, if any. Also, you can transform calibration table between same vehicles with same tanks and avoid tank calibration, but for this, very highly recommended to know real tank volume of all vehicles. For example, you can ask customer to measure it by filling. It's much easier than doing batch calibration by portions. So I'm finished. If you have any questions, you can post in the chat. I will reply. Anyway, you can post questions in comments after this webinar. It will be YouTube video. You can post your questions in any time. Thank you.